Okay, so we're talking about a mass spectrophotometer and how it works. And so we're talking about the graph of percent relative abundance versus the mass charge ratio. And we can see for this element, zirconium, how it has 5 different isotopes. And we can see the values of the relative percent abundance here are different for each isotope. Of course, we know the relative abundance, the percentage, should all add up to 100%. And so, of course, the higher the value, the more common it is in the sample of zirconium. So we can see that zirconium-90 is more prevalent. And so it's the most common form or isotope for that element. And then we can see these other isotopes, zirconium-91, 92, 94, 96. So you can take a sample of zirconium and then you end up getting out the types of isotopes for that element. Now we're going to talk about molecular versus empirical formulas, and then talk about bonding arrangements of atoms within molecules using structural formulas. Okay, so first we're going to talk about molecular formulas. The molecular formula is pretty much what you're going to be looking at mostly this semester. So it represents a molecule or a compound that consists of the following chemical symbols that indicate the types of atoms, and the subscripts, of course, tell you how many atoms there are for each type of element. So subscripts are used only when more than one atom of a given type is present. So that means that if it doesn't have a subscript, it's assumed to be 1. So if you write the symbol, it's written there for you, or if you write it, it means there's only 1 atom. If you need more than 1 atom for that element, then you're going to have to add a subscript 2, 3, 4, etc., however many atoms you have for that element. The structural formula shows you the same information as the molecular formula, but also shows how the atoms are connected. So here we're going to see an example of a molecular formula. So we talked about this before. So here we have CH4. This is called methane. It's its common name. So notice there's no subscript after the capital C. That means there's 1 carbon atom here. And there are 4 hydrogen atoms. Okay, so CH4. This is called the molecular formula. This is what we mostly use in this course. B is a structural formula. Now, you're going to get a lot more experience looking at structural formulas when you take organic chemistry. So the difference between a structural formula versus a molecular formula, a structural formula is going to show you how the atoms are connected together. You see there's a line in between C and H. C, of course, represents a carbon atom. H represents a hydrogen atom. The line in between them represents the bond that's occurring between the carbon and the hydrogen atom. And so notice you have one line here that represents a bond. So it means there's a covalent bond between carbon and hydrogen here and here and here and here. So every line represents a covalent bond between the 2 atoms. So part C is referred to as a ball and stick model, and if you have sometimes you can get these kits, these 3D kits where you can make ball and stick models, or you can make space fill models. The ball and stick model is kind of exactly what it is. A ball represents an atom, the stick represents the bond between 2 atoms. Okay, and you can see it here. Now, what's unique and nice about this is in 3 dimensions. All right, structural formula, it's really hard to see that the molecule's in 3 dimensions. You use a ball and stick model to show you basically the molecular geometry that the molecule has. And so this is referred to, in this case, this is referred to as tetrahedral. And we'll learn a little different molecular geometry a little bit later this semester. And then part D is a space field. And so the difference between the space field model and the ball and stick model is the sticks are no longer there. They're very short. They're shortened to where you really can't see them. Okay, and so it looks a little bit different in that case. All right, so many elements consist of discrete individual atoms. Some elements elements exist as molecules. So there's these types of molecules called diatomic molecules. These are very important. There's 7 of them. Okay, so there's 7 of them, and they're important because they don't exist by themselves. So we breathe in molecular oxygen, right? We do not breathe in O, or oxygen. We breathe in O2. Oxygen does not exist as a single element. Okay, it exists as a molecule if it's by itself, which is O2. So what we breathe in every day is O2, not O. Okay, O does not exist. You can have H2O. You can have one atom of oxygen if it's combined with another element. But if it's combined with itself, it has to be O2. Okay, it's not going to be found as just oxygen. And so that's the case for all these diatomic molecules. You need to memorize them. When we start to write chemical equations, and I say you added oxygen or you added hydrogen, you're not going to write plus O, you're going to write plus O2. You're not going to write plus H for hydrogen, you're going to write plus H2. Okay? And here's just a side note here for sulfur, it exists as S8. Okay, by itself. So here I wanted to bring in the periodic table to show you an easy way to memorize your diatomic molecules. Hydrogen is one of them, and then it kind of makes, there's 7 of them, right? So 6 of them line up in the shape of a 7. So nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2, bromine Br2, iodine I2. You see how it makes like a little 7, and there's only 6 of this 7 that make up the 7, but hydrogen is included in that. Okay, so that's one way you can memorize your diatomic molecules. All right, so here we said that sulfur exists as S8, and so here we can see the structural formula represented there. And then the ball and stick model, and you can see, of course, this is in 3 dimensions, so it's a lot easier to see like in person because, you know, this is a flat surface. But anyways, you can see the sort of the geometry there, and then the space filling model as well. All right, so here we're going to look at how we write chemical symbols, okay, and the numbers associated with them. All right, so for one hydrogen atom, it's just going to be a capital H. Okay, so we're talking about chemical formulas here. 2H refers to 2 hydrogen atoms. H2, notice the 2 is at the bottom. It's a subscript. This is a hydrogen or H2 molecule. It means there's 1 H2 molecule. And then 2H2 means there are 2 molecules that are hydrogen diatomic molecules, H2. So when you have a coefficient, that represents how many atoms or molecules you have. If you have a subscript, that represents how many atoms there are that for that element. All right, now let's define empirical formula. So empirical formula indicates the simplest whole number ratio of the number of atoms or ions in a compound. The molecular formula indicates the actual number of atoms of each element in a molecule of the compound. So here we have what we just defined here. Basically, what you need to think about when you talk about a molecular formula, pretty much that's what we're going to be talking about this semester, okay? So what's the difference between that and an empirical formula? An empirical formula, you can think of it as being sort of like a simplified form of a molecular formula. Sort of like if a person's named Christopher, sometimes people just call them Chris, right? If you have a nickname or it's shortened. An empirical formula is sort of that way, okay? It's sort of the nickname of formulas, all right? It's not going to tell you everything. It's going to tell you the simplest whole number ratio of the elements. It'll tell you which elements are in that compound, but it's just going to tell you the simplest whole number ratio for those elements. It's not going to tell you everything. The molecular formula tells you everything. Well, technically not true, but I mean, in this part, mostly yes. I mean, I prefer structural formulas to tell you a lot more than molecular formulas, but in this course, we're focused mostly on molecular formulas. So, anyways, comparing the two, with our molecular formula here we have for benzene is C6H6, our empirical is CH. Okay, so how do we do that? So I'm going to show you an example where we can figure that out. So basically all I have to do, I'm going to tell you verbally, and then I'm going to show you some examples doing some problems later. So if we take 6, divide each of these by 6, we get 1, right? 6 over 6 is 1. And so the simplest whole number ratio would be C1H1, or just CH. For acetic acid, we have C2H4O2 for the molecular formula. The empirical formula, if we take 2 and divide it by 2, we get 1. 4 divided by 2, we get 2. 2 divided by 2, we get 1. So the empirical formula is going to be CH2. Okay. Here's a picture of, here we have titanium dioxide, and it's found in sunscreen. And so here we have some pictures of titanium and oxygen in a certain ratio. So for titanium, for every 1 atom of titanium, you have 2 atoms of oxygen, TiO2. Okay, so TiO2, titanium dioxide, is the molecular formula. In this case, titanium dioxide is also the empirical formula because there's no number I can divide by that would reduce the subscripts down, right? TiO2. So, they're both, sometimes you get in the case where the empirical and the molecular formula are the same. Another example, H2O. H2O cannot be, the subscripts cannot be simplified any further, and so its molecular and empirical formula are the same. Okay, here's benzene. Here we have the structural formula for benzene, and then a ball and stick model, and then a space filling model, and then a picture of benzene here. So benzene, its molecular formula is C6H6. We can divide both of these subscripts by 6 to get CH. That would be its empirical formula. Vinegar contains acetic acid, C2H4O2. Here's the structural formula for it, okay? And then here's the ball and stick model here. And again, the ball and stick model is helping you visualize what it looks like in 3 dimensions and this geometry. And so we can simplify acetic acid into its empirical formula, which is CH2O. Of course, we're dividing all the subscripts by 2, right? 2 over 2 is 1, 4 over 2 is 2, 2 over 2 is 1. So CH2O is the empirical formula. All right, so let's go over this problem here. Example 2.6 and the Check Your Learning example. We're going to do both of those from your textbook. Let me bring up your textbook here. We're going to go to the next section. And so here we see an example of empirical versus molecular formulas. So here it says molecules of glucose contain 6 atoms of carbon, 12 hydrogen atoms, and 6 oxygen atoms. What are the molecular empirical formulas for glucose? So here they pretty much gave me the molecular formula, right? So it said 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. So that's the molecular formula. And so the empirical formula, I have to figure out what number I can divide all of these by evenly. And I'm looking for the highest number, not the lowest. So here I could use 2, but it wouldn't be the empirical formula because then I could reduce it again, right? So I use the highest number, so 6 would be the highest, so 6 over 6 is 1, 12 over 6 is 2, 6 over 6 is 1, so our formula here for our empirical formula for glucose would be CH2O. And you notice the empirical formula can be the same for different molecular formulas, because this was the answer for another problem we had earlier. All right, what about the Check Your Learning question? C8H16O4. So again, this is its molecular formula. How do I figure out the empirical formula? Again, I'm going to look at the subscripts and figure out which number I can divide by. I can divide by 4, okay, and it'll divide evenly. So 8 divided by 4 is 2, 16 over 4 is 4, and 4 over 4 is 1. And so my empirical formula is C2H4O.